Well, here we are, April the 16th, 2020 lesson. Hope everybody's doing well and making it through this tough coronavirus episode we got. I've never seen anything like it myself, and I'm sure y'all hadn't either, but there's no recipe for it. We just working our way through it and trying to be as clean and safe and not spread it to our family. I've got some older parents and I don't want to give it to them, so I've been kindly staying away from everybody, but I am having to go get groceries and getting out and doing a few things. But anyway, the lesson for today, 4/16/2020, is going to be term 1 review. So this is the 5th week of at-home training, so I hope everybody's doing their questions and answering everything and staying up to date. If you haven't turned in your chapter questions, please do that so everyone will be caught up when we're able to start back. I'm hoping that'll be the 1st of May. I haven't heard anything official. I'm sure they'll tell us by email. But anyway, we're just going to keep right on going. I'm going to do a video. I'm going back to the course schedule. So if you've got a course schedule, you'll be able to look at each week and see what we studied. Go by that. Look at your questions and your answers, and just go back and get re-familiar with the material. Let's see here. They're going to be from, first of all, going to do a OSHA safety lockout, tagout. I think that's a very important procedure that not everybody I hate to say this, but not everybody goes by it. If you're especially in a phase where equipment's running and can move and turn by hydraulics or electrical or air or any kind of motion, then certainly need to put a lockout tag out. And even if it's not labeled good, it should be, but even if it's not, if you have a lock on it, if you're working on it with only your key, nobody can take it off. It'll raise somebody's attention. So we're going to start out and do a video on that, and then we're going to continue right on into power quality with some PowerPoints. And I'm going to go ahead and start this.
Energy. It's essential in the workplace. Because energy is always around us, we may take it for granted and underestimate the potential hazards. Accidental release of stored energy can happen in a second, but the injuries can last forever. The good news is, when proper safety procedures are followed, these accidents are preventable. That's the purpose of a safety lockout-tagout program. Let's take a deeper look at lockout-tagout, why we need it, who's affected by it, and the steps to safely apply and remove lockout devices to isolate hazardous energy prior to and after equipment servicing and maintenance. A wide variety of machines and equipment is used daily in industrial environments, but never forget the potential danger. Machines require energy to operate. Energy that's potentially hazardous to workers if not properly controlled during maintenance procedures. The consequences can last a lifetime. Hazardous energy comes in many different forms, such as electrical, mechanical, hydraulic, pneumatic, chemical, thermal, or other energy. All these energy types can unexpectedly start up equipment if not controlled. That's why the energy sources need to be identified and locked, blocked, or released before anyone services the equipment. Each year, nearly 10% of all serious workplace accidents result from the failure to properly control hazardous energy. In fact, failure to correctly perform lockout-tagout ranks in the top 10 citations every year. To help keep employees safe, lockout procedures are a combination of processes and products to isolate energy sources to machinery. Lockout procedures keep equipment energy sources from activating when you don't want them to, especially during maintenance, where employees are vulnerable to injury or death. In addition, effective lockout-tagout procedures minimize downtime and protect expensive equipment. Procedures ensure that machines are correctly shut down and restarted, avoiding equipment damage from incorrect shutdown or unexpected startup. The federal law that governs lockout-tagout is an OSHA standard for the control of hazardous energy. The law spells out requirements to disable equipment and prevent release of stored hazardous energy during maintenance. The primary focus is on general industry, but the OSHA standard also applies to other work environments. OSHA has specific standards for marine terminals, longshoring, and the construction industry. In addition, other industry-specific safety organizations exist, such as MSHA, the Mine Safety and Health Administration. The OSHA standard applies to businesses in any of these situations. When an employee is required to remove or bypass a guard or other safety device. When an employee is required to place any part of their body in contact with the point of operation of the machine. Or when an employee is required to place any part of their body into a danger zone associated with a machine operating cycle. OSHA has established the following general guidelines for lockout-tagout devices. Lotto devices must be manufactured from durable materials to withstand the industrial environment of their use. They must be substantial enough to prevent removal without the use of excessive force. They must clearly identify the employee who installed the device. They must be standardized within the facility by color, shape, and/or size. They must be singularly identified. Only lockout-tagout devices are to be used to control energy. And lockout-tagout devices cannot be used for any purpose other than controlling energy. Never use them to lock a toolbox, locker, storage area, ladder, or other items. Lockout impacts a variety of workers at a facility. The three categories are authorized employees. These are the workers specifically trained to lock out or tag out equipment in order to service or maintain the unit. Affected employees are the ones who work with or near the equipment being serviced. They are trained to recognize the lockout but not perform it. And other employees are those who work in or near an area where lockout-tagout may be used. They also need to be instructed to recognize lockout but not perform the lockout procedure. There are four key components to an effective energy control program. Beyond having sufficient safety padlocks and lockout devices on hand, there needs to be machine-specific lockout procedures, inspections, audits, and employee training. Machine-specific lockout procedures outline the specific steps and requirements that an authorized employee needs to complete to safely lock out a piece of equipment. This includes posting the procedure at the equipment location for easy reference. OSHA requires annual inspections and audits. Inspections ensure that employees are correctly following the energy control procedures. Audits verify that the written procedures correctly describe the steps to isolate the equipment's energy sources. And the fourth element of the program, employers are required to train their employees to make sure they understand and can follow lockout procedures. Retraining is required to maintain proficiency. Whenever an employee has a new job assignment, whenever control methods change, such as new steps due to equipment modification, revised steps for a procedure change. Every piece of equipment must have its own particular procedure for lockout. It may mean locking out a circuit breaker, locking a valve in the off position, or using a disconnect switch, to name a few. In general, there are 7 steps for safe lockout-tagout. First, prepare for shutdown. Locate all the energy sources that power the equipment. Each source is identified on the machine's lockout procedure. Next, notify all affected employees that you're ready to start a lockout procedure. Step 3. Stop the equipment by following its normal shutdown procedure. Step 4. Isolate the equipment by turning off the energy at the main power source. Step 5. Apply a lock and appropriate lockout device to each energy isolating device. Each lockout point that is detailed in the lockout procedure. For example, a gate valve needs a gate valve cover. The lock or tag that goes with it must clearly indicate who applied the lockout device. If several people are going to work on a piece of equipment, each one must apply his or her own lock to the isolation device. This ensures that the energy source will remain off until each employee removes his or her lock. Step 6. Release or secure any stored energy. This may involve draining valves, releasing hydraulic pressure, blocking moving parts, or however it's detailed in your company's procedures. Step 7. Verify the power is shut off by trying to restart the machine. Once verified, return the machine's switch to the off position. After the service work is finished, there are 5 steps to release the equipment from lockout-tagout. First, make sure all tools have been removed and all machine guards are back in place. Check that all employees are clear of the machine. If you can't see inside a piece of equipment, take a head count. Remove the lockout-tagout devices. Each person must remove his or her own lock and tag. Before you restart the equipment, notify all affected employees that the lockout-tagout devices have been removed. And finally, restore energy to the equipment in the order indicated by the lockout procedure. A high percentage of accidents happen just after shift changes. It's often due to a lack of communication. That's why you should meet at the lockout-tagout device with the person you're relieving. And then, before you leave, meet with the person who's relieving you. In general, if a piece of equipment is locked out at a shift change, the person on the next shift has to apply his lock before you can remove yours. If for some reason the person who applied the lock is not available, the supervisor may remove the lock and tag by following the company's pre-established written procedure. The supervisor must verify that the employee who applied the lock is not at the job site and make reasonable efforts to reach the employee. Before that employee returns to work, the employer must let him know the lock or tag has been removed and the equipment is no longer de-energized. Working around hazardous energy can be safe, but only when everyone takes responsibility for their part in the safety lockout-tagout program. It starts with the employer, who establishes the safety lockout procedures and conducts training, audits, and inspections. And safety also depends on employees to learn and follow the procedures for lockout-tagout each and every time.
All right, we want you to go home with all of your fingers and toes and life, to go back. We're just working to be able to provide for our family and do things at home. That was always my opinion. I didn't do things at home so I could work more, or you just got to be safe at this any kind of job you're doing. But electrical work is really dangerous. It gets into other stuff, moving parts, hydraulic, air. So just be careful out there on the job and really think it through and try to look ahead to stop a potential problem or an accident from happening. I'm going to see if I can't make it to the PowerPoints. Let's see. I think Mike Holt does a good job at trying to get across the electrical training. He is a Christian man, and I think he's he come up like we did out in the field and seen a need for people to get on the same track as far as what the code book says and what's actually working out in the field. I think he does a good job at it. So, he's says right here he's dedicated, and that means a lot. And we're going to ease right through this and see how this works out. See, the power quality. I never really thought about power quality until I got into really maintenance. When I was in construction, I really didn't think about the noise and what problems it would cause. But it does come into play when you talk about neutrals and grounding and operational problems. Poor quality can also lead to serious safety issues. So, distribution systems which are properly designed and installed should provide safe, clean power, which reduces operating costs, minimizes maintenance issues, and improves employee productivity. Basically, improves the bottom line, which that's what they're looking at. You can tell right here the disruptions it would cost you. That's important, very important out in the workplace and at home. Let's see. There are many factors that degrade power quality. The most significant includes voltage and current disturbances, poor system design, field wiring errors, and improper grounding. Never thought really on the neutrals and the grounding being such a problem until later on in my career, and it is really important. The movement of electrons for production of work can be compared to the movement of water. Let's just go through some of them. It's a good analogy to look at the electrical circuit. In your mind, you have to have some kind of vision because you can't see the electricity. But this is a good thing to have in your mind for AC, closed loop system. And it's actually coming from most of your power. If it's not coming from a nuclear or a coal fire, it's coming from a dam. So that's a good way to look at it. Electrical current flows from the power source through the equipment, and then it returns to the power source. This path is called the electrical circuit. We just want to keep it pretty simple. I've always thought this and read it, but in my mind, it seemed like it should go the other way. But according to the electron current flow theory, electrons flow away from the negative terminal of the source through the circuit and load toward the positive terminal of the source. I always looked at that backwards. I'm not arguing with the fact that this says this, and I agree with it, but in my mind, I just think about it going from positive to negative for some reason. According to the electron current flow, electrons flow away from the negative terminals through the circuit load toward the positive terminal of the source. For current to flow, the power supply must apply significant pressure to cause the electrons to move through a closed loop from the source through the load and then back to the source. So it's got to have something to apply the pressure that causes electrons to move. And the volume of electrons, which is the current that can flow through a circuit, depends on the circuit pressure, voltage, and the circuit's opposition to flow of electrons, which is resistance. The more you talk about it, the more you kind of get it in your mind what each item represents, like current and voltage and resistance. Ohm's law. You don't have to memorize this Ohm's law, but you need to know what to do to solve electrical problems. It's the most important one that I've used through my career, and it's not that hard. You just need to be able to know the relationship between voltage and current and resistance, and it can be demonstrated, and you can prove one or find the other one with two known laws. So just really study that Ohm's law and know how to use it. Here it is again. You can see as he's putting his thumb over what he wants to know, you can do the equations from the other two. So if you have two known factors, which you most of the time always do, if you don't, you have to research to find out, because that's the only way you can get there. But you put your thumb over the unknown symbol, and you can do the equation for the known and come up with the answer. The voltage of a circuit is distributed across all components of the circuit, such as the power supply, circuit conductors, load, loose terminals, in proportion to their resistance to the entire circuit resistance. If you have a loose connection, it's going to make a difference on your load. A lot of things vary. The voltage of a circuit is distributed across all components, such as power supply, circuit, load, loose terminal, in proportion to the resistance of the entire circuit. Here's a good example, and they're actually looking at the voltage drop. You don't have to memorize all this stuff, but you need to be able to solve the problems by knowing these facts. Alternating current produced by an AC generator consists of a loop of wire having relative motion to a magnetic field. Relative motion to a magnetic field. This, I always think about this on using a magnetic coil, is a solenoid. And a solenoid if you're going to like have a water solenoid to turn it off and on, it uses a magnetic. The valve will be under the solenoid, and it'll have a coil that comes up, and when you apply voltage, it'll move the shaft one way or another to turn it off and on, and it picks up the shaft, which opens the valve. It's a good example of using a magnetic coil, and also on a motor starter. If you apply voltage on a magnetic coil of a motor starter, it pulls the starter in and then makes your contacts make your line to your load. So another good way. There's an alternating current generator, and it's putting out AC. So if this motor is run by gasoline, it's turning the motor, and through the windings and the loops and the magnetic field, it's outputting AC voltage. I tell you, I wished I'd have been the one to come up with it. It's all over the world, and everybody uses it. The output voltage waveform from an AC generator having a symmetrical shape with positive above and negative below the zero reference level is called a sine wave. So you have your sinusoidal waveform, and you just look at zero reference being the center, and when it goes above, it's positive, and below, negative. And since you can't see it, it's a way to hook up an oscilloscope and see what that wave is doing. When you get deep in it, like for drives and filters, electronics, you're looking for these waveforms, and you're making them do work. And the only way you can troubleshoot it and make it and dial it in to what you want it to do is with a oscilloscope. There's your line, your zero line, your positive and your negative. And that 360 degrees is one rotation. When that shaft rotates in that generator one time, that's what that sine wave is doing in that generator output. The number of degrees of a full waveform is 360. That's a full circle. Shows you degrees on your poles. That would be in the generator itself. So one full circle is going to go positive to negative in the degrees of the waveform. Important AC waveform value include peak, RMS, instantaneous, and zero voltage crossings. So you can take a device and it will look for the peak or RMS or the voltage zero to do whatever work is it needs to do. There's another sinusoidal waveform values. The peak value of a sinusoidal waveform will be 1.4 times the root mean square RMS value of the waveform. For example, peak voltage is 120 volts. The circuit would be 170 volts. It'd be 120 times 1.4. Unless you're trying to figure out a engineering problem, you won't be concerned with this, but it doesn't help in your mind to know what they're talking about when you're talking about RMS and peak. So your RMS, root mean square value, is going to be lower than the actual voltage would be, which is peak. I'm going to move on down to, all right. All your electrical circuits out in the field are identified as RMS voltage. And when you walk up to a tag on a panel, that's what you're going to see. So it's 120 volt, 208, or 277. That's your RMS. And you would have to do the formula for your peak. But we're not worried about that. You might have it on a test and know how to come up with a formula, but we're looking at RMS voltage. Zero voltage crossings. It crosses it twice in each cycle. Here's one, and there's another one. That's your 360. One revolution. All right, if you have some large loads, they can create additional zero voltage crosses. Well, if you've got a device that's looking at how many times that voltage crosses zero, it could give you false readings. And sometimes they use that like for counters and other devices, but large loads, you have to use some electronics to filter out those notching. It shows some of your notching right here. Normal zero crossing is at 180, but it crossed it here 1, 2 times. So you would have 1, 2, 3, 4 crossings if you had a device that was counting the times that the sine wave went to zero. There's your non-sinusoidal waveform. The voltage or current waveform that is not a sinusoidal shape with positive above and negative below the zero reference level. Here it is, for example, your peak again. The peak is 1.4 times greater than the RMS. Just remember, if you're in a conversation, they talk about peak. They're not talking about the peak as being 120 or 480. They're talking about the peak is 1.4 times greater than the RMS. If you read, your voltmeter is going to read RMS, your fluke or whatever you got. All right, the frequency is the number of complete waveforms, 360 degrees per second expressed in hertz. Anything we have in the United States is going to be 60 hertz. If it's coming out of a powerhouse, a dam, or a nuclear, they're putting it out in the world, in the United States at 60 hertz. Now, if other countries, I think they have some 50 hertz. Not really sure, but sometimes they don't put out on, I don't know really why. Have to look that up. But there is 60 hertz is 60 cycles per second. There it is. In the U.S., power supplied by electric utilities is 60 hertz. So that's good to remember. There's a picture of the dam. got an opportunity to go to down in Mississippi and see the Wilson Dam. It is was built back in the around 1918, before World War I. And it is a very big dam and a lot of water coming through it. It's very powerful. I would like to take a trip through there and tour through there and see everything on that dam. But it's down around Muscle Shoals. If you ever get a chance to go down there, they got a Marriott that's set right on the bank, looking right into that dam. It's a nice place to visit. You get into the phase, and when two sinusoidal waveforms are in step with each other, they both reach their zero and peak values at the same time. You can tell they're together here, they're back together here. And when they do that, they're said to be in phase with each other. If they're out of phase, they reach their zero and peak values at different times. They're said to be out of phase when this happens. And here's an example of that. Eddy currents, electric current induced in a conductor due to the expanding and collapsing alternating magnetic field within the conductors are known as eddy currents. I'm going to move through this capacitance. A lot of motors, especially single-phase motors, a lot of equipment, air conditioners, compressors, different things like that, they have capacitors in them to help them get started. But capacitors are electrical devices that store energy in an electric field between closely spaced plates and are capable of releasing the energy at a later time. And you can just tie that capacitor right straight to the line. If you had 480 there, they make 480 volt. You have to have the rated capacitor, but you put it on there, and at any given time, when that capacitance needs to be released into the circuit, it will do so. That's kind of wild, but that's how they help the lead and the lag of your power factor, so that you're using good electricity. There are good electricity and bad electricity that you use, and the more good electricity you use, the less you have to pay for. So it's capacitance is very important in a circuit. There's where the plates are, and they're showing this in DC, but you have AC capacitance too. You get into the reactance and the inductive reactance. Resonance occurs when inductive reactance and capacitive reactance are equal. All right, we're into neutral conductors. The conductor connected to the neutral point of the power supply, which is intended to carry a neutral current, is called the neutral conductor. If it's carrying current, it's got to be insulated. So there's your difference between a current carrying conductor and a ground. The ground don't have to be, but you also don't want current on your ground. So it's important to keep separated a neutral conductor and a grounding conductor. The current flowing on the neutral conductor will be the same as the current on the ungrounded conductors. There's the neutral for a 3-wire single-phase circuit. These are some good examples of looking at what that neutral. The currents cancel because the currents flowing through the neutral conductor at any instant from the ungrounded conductors oppose each other. If the ungrounded conductors of a multi-wire circuit are connected to the same phase, the current on a neutral conductor will not cancel but will add, which can cause an overload on the neutral conductor. So you have to be careful of how many neutrals are on the same circuit. So right here, if they're on different circuits, they'll cancel out. But if they're on the same circuit, L1, off that one lead, then you got 20 amp breaker and a 15 amp breaker, and you loaded with some kind of heat or whatever was pulling 35 amps. If they were loaded up, then you would have 35 amps on your neutral. A lot of times you can go to a neutral, and if it's been hot, that's what they've done. So be careful how I a lot of times just pull one neutral to one phase, and that way I'm covered. But if you go to hooking up several circuits and using one neutral, be careful about that. Harmonics. That's the load in which the current has the same waveform as the voltage. Linear load. I'm not going to go over a lot of this. If you have a test question, you'll have to go back and look it up. It's more of the same signs and looking for constant impedance. Now you get into some nonlinear loads. Can include like fluorescent lighting, HID lighting, electronic ballast, dimmers, motors, frequency drives, computers, UPSs, printers, other equipment. Might not pull the same thing. Here's some of your voltage distortion. Gets into flat topping, notching, extra zero crossing. We talked about that earlier. Spikes, surges, sags, over voltage, under voltage. All that is really hard on your electrical system and your household items or commercial or industrial items, refrigeration, motors, lighting. It can really damage equipment. Voltage sag is a short duration decrease in voltage caused by a short duration increase in current flow, such as a motor starting. So everything's rocking along and everybody's doing good, and all of a sudden your lights dim, and maybe in a plant you see the lights dim and flicker. Might be because they started up a big motor. Well, that big motor took a lot of energy and voltage current draw, which caused the voltage to sag, and there you go. It starts having problems from there. Then after a little bit of time, it straightens out. If your system can stand it, it don't cause problems. If not, you have problems. Under voltage. Voltage sags of more than 3 seconds are classified as an undervoltage condition. The most common cause of undervoltage is excessive conductor voltage drop, open neutral of a multi-wire circuit, and loose terminals. Loose terminals, probably the most common source of voltage sags in the country. That's just saying the electric utilities permitted no more than 10% from normal voltage. NEC recommends no more than 5% voltage drop. Nominal system voltage for feeders and branch circuits. Over voltage, when a neutral conductor of a multi-wire circuit is open, the voltage across each load on each circuit will become unstable. Very unstable. Transient, sometimes called voltage spikes, caused by the switching of utility power lines or power factor correction capacitors, or lightning, can reach thousands of volts and amperes. Happens a lot. There's some of that corrective capacitance. If you have a power factor corrector bank, it sees the voltage and it sees it needs more capacitance. It throws in starters to add more capacitance to the line, and sometimes it can spike the voltage. Surge protection devices. Just about all your factories have your surge protection for spikes and lightning, and usually it will have a set of contacts that will tell you if it's open or closed. And if it sees I know a lot of the water and wastewater devices or pump stations have a surge protection and just a phase monitor. If you lose a phase, it will drop your controls out, carry your control voltage through that device. And if it loses a phase on a 3-phase system, it will drop that control voltage out and open up all your starters where it don't damage your motors. Electrical noise. Still the same. It's affecting the wave form and induced from electric motors and motor control, electric furnaces, welders, control relays. They're classified as electrical noise depending on, like I say, I have a CB radio and my lights are LED lights, when I turn them on, they got so much electrical noise in my CB, I can't talk. So I have to use a lamp over to the side, turn my LED lights off before I can talk on the radio or listen to the radio. See the choppy sine wave from electrical noise. That's a bad thing when it comes to sine wave. See there, they're telling it right there. Noise can be picked up in a computer network, communications equipment, AV equipment, and telephone systems when harmonics are at audio or radio frequencies. Metal conduit, shielding. Most all your equipment rooms, you might see a little flex in there, but most of your conduits, steel conduit, and it reduces electromagnetic fields by up to 95%. That's a good thing. And just about all your motor control centers are run in conduit for that reason. If you've got a cable tray, a lot of communication, computers, cables, they'll still use shielding to help reduce the frequency interference. Grounding and bonding. All systems are either ungrounded or grounded. The advantages of grounded systems is that they help reduce equipment damage and fires from lightning and restriking ground faults. Very important. Right here it's saying grounding is not, never thought about that, but that's a doorbell. That's a simple little old doorbell system. There's your chimes, and there is your push button at your door. The grounding is not required because it's operating below 50 volts. Now, what happens if you get a lightning strike? I don't know. I guess you'll be replacing the doorbell transformer. That's 120 volt to 24 volt. It'll probably take out your chimes or your push button, but it doesn't require ground. To minimize fires and electrical shock or electrocution from lightning induced voltage, all metal parts of electrical installation must be bonded together and grounded to the power system earth ground. Metal parts are connected to earth to limit voltage from lightning and other high voltage surges, not to clear a ground fault. There's what happens when that equipment grounding can help reduce damage from lightning. I've actually seen stuff like this happen. I've seen it blow out every receptacle in a room. And I also seen it blow off a 200 amp panel cover. The lightning struck the corner of the house on a 2-story house, and the 200 amp panel was in the carport opposite end of the house, and it caused a lot of damage. We worked a lot replacing bad stuff that it jumped on and something, and it was grounded properly. You can't stop all of it. Big storm cloud right there. Be time to run. There's where they're talking about current. See, he's on a ground, and he's got current. Electrical systems and equipment must be installed in a manner that prevents objectionable current from flowing on a conductive parts. You don't want it flowing on grounded. Quality power. We got into a lot of adjustable speed drives, AC variable speed drives. A lot of that in the motor, in the water and wastewater industry to run motors, because you want to run them different speeds at different times. Overcurrent protection for power factor correction. Capacitors opens prematurely. Capacitor failed when the capacitor become tuned to a specific harmonic. There's what it looks like. There's your capacitors. And that one blew up. Inside of a breaker, overcurrent protective device. Lights flicker. An electrical contractor is sued by a homeowner because their incandescent lights flicker when AC starts. Solution? Not much. Ain't much you can do with that. They need to explain that to them on the front end. Transformers. Transformers often fail because of inductive heating from circulating eddy currents, hysterics, and an additive tripling harmonic current. See a lot of UPSs, uninterrupted power supplies. We used to use them so that if you lose your AC on like a computer or PLC, the UPS would hold it up we could communicate, and we would have a set of contacts on the AC side so we'd know it was down or up, but we could keep communicating with the SCADA system by UPS. It would hold it up long enough. Usually the electrical guys would get it serviced back up, get power back on. So a lot of power supplies used in the water, wastewater. All right. Y'all, if you would, this is a review, and next week we'll have a term 1 exam. I'm not sure about how we're going to go about that, or if I'm going to get the questions or go out of the book. But just review, watch this video, and go over your course schedule all the way up to April the 16th. Review your questions and answers. And if you hadn't sent them to me, some of you sent them in. If you hadn't sent them to me, I would appreciate you doing that so I can get caught up on the checking them. I'll send you feedback. But again, guys, I look forward to us meeting back at school. I don't feel like we're getting the one-on-one and the personal training that we could be getting. And after, let's see, we get into May the 7th, I'm hoping we'll be able to go back to school then. But then we'll get into motors, motor controls, and controllers. That's really something we need to be together and use the trainers in the lab. But we will make it through it, and hopefully we will all learn something from it. And if you have any questions, give me a call. Don't hesitate, and just keep me informed and keep in touch. Y'all work safe and be careful.